Pushing water through a long pipe naturally loses pressure due to friction. In the same way, pushing electricity over hundreds of miles usually results in a loss of power, a slow drain known as voltage drop, caused by natural resistance. Imagine a massive factory at the absolute end of a 300-mile power line. At 5 p.m., the shift ends, and operators shut down all the heavy machinery. You would expect the electrical line to relax and go quiet. This chart compares the voltage at the sending power plant to the receiving factory. As the factory powers down, the receiving end voltage actually shoots upward, spiking much higher than the power plant that generated it. Engineers call this counterintuitive spike the Ferranti effect. It happens because these long-distance wires behave like a complex machine, even when they appear to be idle. A transmission line behaves as more than a simple delivery tube. Its physical geometry gives it a property called capacitance. Think of this as a passive power reservoir. Building this reservoir only requires two conductive plates separated by a non-conductive insulator. The electrical grid directly mimics this model. The suspended metal wire acts as one conductive plate, the earth below acts as the second plate, and the open air between them serves as the insulator. Because of this geometry, the transmission line constantly pulls and holds an electrical charge along its surface. So even when a power line appears perfectly empty of flowing current, it is actively storing a massive amount of hidden electrical energy. During normal operation, a heavy draw from a factory consumes the stored energy from the line's power reservoir, keeping the system balanced. When that massive electrical draw is suddenly disconnected, engineers call the event load rejection. Without a destination drawing the power, the continuous flow of alternating current, or AC, hits an abrupt bottleneck at the end of the line. This load rejection traps the generating plant's raw energy inside our giant, sky-high reservoir, creating a highly volatile environment within the transmission line. At this point, we encounter the second hidden property of the wire, inductance. This property acts like a massive, heavy flywheel, giving the moving electricity a kind of momentum that resists any sudden changes in its path. Capacitance holds static charge, while inductance provides forward momentum. Cut off from its load, the trapped energy sloshes back and forth. This causes the AC wave to compress and peak dangerously high at the far end of the line. The physical length of the wire dictates the severity of this spike. A longer line provides a bigger reservoir and more momentum, directly multiplying the intensity of the sloshing effect. The Ferranti effect is the result of these alternating forces acting as a giant amplifier when a long line is left unloaded. This grid-scale amplifier targets physical vulnerabilities. Transmission lines rely on specialized physical insulators to keep high voltages from jumping into the metal towers. If left unmanaged, a Ferranti overvoltage physically attacks this equipment, violently arcing across the open air or burning straight through protective shielding. If that insulation fails due to overvoltage, the electricity grounds out, triggering massive short circuits, destroying expensive transformers, and causing widespread blackouts. Grid operators cannot leave long lines to the mercy of nature. They must actively intervene to stop the receiving end from destroying itself. To counteract the Ferranti effect, engineers rely on specific hardware known as shunt reactors. A shunt reactor acts as a giant inductive sponge clamped onto the line, designed to absorb excess energy. Returning to our chart, connecting the reactor neutralizes the slosh and pulls the rising voltage back down to safe levels. The rule for this phenomenon is straightforward. A long AC transmission line, combined with a light load, results in a higher voltage at the receiving end. A modern power grid functions as a delicate, dynamic system. It requires constant, active balancing to survive the physics of its own massive scale.